Hmm. All right, we'll get started here. Good morning, everybody. Um, Welcome to the August meeting of the Seattle Robotics Society. As always, we're recording. We'll stop the recording um, we'll probably pause it during the chat, but we'll record through the presentation, and then after the presentation, we'll stop it. It gets uploaded to YouTube. We also try to capture the notes as well. So if you have some notes, I'll go and grab those notes when we're done, and those usually get posted with the recording. So as always, we'll do our welcome, we'll talk about a little bit of club business, some other notes. We'll discuss today's presentation. Looks like Matthew is already on. Do a virtual around the room, right? Just the normal sharing. And we'll have a short break. It's usually around like 5 minutes till or so, somewhere in that neighborhood anyways, and then the presentation. I have to boogie out of here at noon proper, so once the presentation's over, I'm gonna unless somebody's around that wants to host, I'll boot everybody. But anyways, um, oops, that's not the way I wanted to go. Sorry, forgot. Sensitive mouse. My name's Charles. I'm on the Robothon committee, so normally Steve does the meetings, but he's busy, so I well, he's been busy a couple times. He had a lot going on this summer. Who didn't though? So I told him I'd host a couple of these. So, anyways, as always, please mute unless you're actively sharing or you have a question. By all means, stop me and ask a question. You can drop it in chat. It is hard to like present and watch the chat because it's kind of small on my computer, but please do. I'll try to keep an eye out on that. Um, and then of course, you can always throw comments and questions in there if you have questions, and other members will chime in. In club business, usually Lloyd or I host these. By all means, if you are interested in hosting these every once in a while, we don't want to have a monopoly on it. So you're more than welcome. Just reach out to Steve, or email that email address at the bottom, seattleroboticsociety@gmail.com. If you have interest. We're also always looking for presenters. Um, so that's how you reach out. I don't have any past or recent events to share. We have a couple future ones come up. I'll share in the next slide, but anybody have any events they want to share that they might have gone to, or we missed out on a good time? All right, we'll continue on. There are a few maker spaces out there. The reason we put maker spaces here is because they are good places to meet, like-minded people, and then also build stuff, right? Get ideas on building your robot, either the mechatronics portion of it or the electronics portion. Um, there's Snowco makers in Everett. There's Federal Way maker space in Federal Way. Seattle Makers is in like Wallingford area, Seattle. Alt Maker Space is more, I think, Capitol Hill. I don't remember to be sure on that one, but it's more central. North End Makers is in Shoreline, basically. Creation Stations Tacoma. There's also a like Holy Mega down in Olympia. Um, and then you can always go to makerspaces.make.co, and they have an okay library. Not everybody puts their maker spaces on it, but it's pretty decent. There's some old ones in there still, so be wary of that. Maybe go look at their website to see if they're still around. There's also one up in Bellingham in the mall up there, and that's a pretty big size one. I think there's 7,000 square foot. So move along past that. If you have any others to share, by all means, please drop them in the chat. We'll try to get them added to the list. Events coming. As always, you can see the robotics event website for national events. There's meetings and Sunoco Makerspace. I should have edited this, but it's there in South Everett, right off like 128th. So that's just on the border of Linwood and Everett. There's Pratham AI hackathon demos, which are I don't know. Oh, I see. They're July through September. I don't know much about those, and there's not a link there. And then there's the SRS, Seattle Robotics Society's Mini Robothon Plus, and that's coming on October 12th. We just got the space or the field secured. It's going to be at the same place as it was last year. There's more information to come about that, but there is. Let me see if I can find the right browser real quick. This one, I think. There is the robothon.org website, robothon.org. It's been updated, and there's, I guess, the registration. I don't know if it's quite up yet, but it's there. It's ready to go. As you see, we're going to have Mini Sumo. We're going to have the SRS build challenges 1, 2, and 3, and then the SRS Robo Magellan. So those are all, Mini Sumo isn't outdoor. It can be done anywhere, but mostly it's the outdoor events in this case. So yeah, you don't need to register to be attendee. We're doing something a little bit different this year. I mean, it's probably more harkening back to the past, but they are having some presentation tables, like display tables. So you don't have to necessarily like compete to show off your robot, particularly those that don't build competition robots. All robots are fun robots to build, but we'll have some display area. It doesn't cost any money. Just mention that you need some space. I'm not quite sure. There's details coming soon, but you'll be able to display your robot. And if you're interested, have a talk about your robot there. Maybe have an actual panel or whatever while we're there. So keep an eye on this. We're still planning. We understand it's October 12th, so it's kind of coming up soon. That's 2 months away, but still keep an eye on that. And then, as always, reach out for questions and see if I can find my share again. This one, maybe? No. I'm gonna have to find this Alt tab. Sorry. Where did you go? All right, I guess I just have to go back and suck it up and exit this. So slideshow. All right, continuing on. If you know of any other events coming, by all means, drop them in the chat as always. And then if you have any other, well, I guess there's a question here probably from Donna. If you have an interest in one of those virtual Robothon exhibitions, that's where, it's a special Zoom meeting just for showing off your robot. Again, not necessarily a competition robot or anything particular, maybe even not something somebody would call a traditional color robot. Even, if you're in the idea station or whatever, reach out to Seattle Robotics Society at gmail.com. Let me get the rest of my Zoom stuff up here. There we go. The Robothon committee, I guess this is just left over from our next meeting is early September, I think I saw, but I think that'll be the final meeting for us in the committee just for setting up this February event, or sorry, the September event. Pretty well got it all figured out though. Looks like Lloyd did a lot of work on getting the space and making sure we had all the tables and chairs and everything. So thanks to Lloyd, even though he's not here today. As always, we are looking for presenters. Thank you, Matthew, for presenting today. They're online presenters, so they can be from anywhere, anytime. We understand international presenters might need an alternate meeting time. We can move the meeting time if needed. Just, when you're reaching out to them, check the time zone. We do ask, we encourage you to reach out to somebody directly, but please include the Seattle Robotics Society at gmail.com and the address of the CC just so that we can be in the conversation when we're setting it up and planning and everything. So, and as always, we encourage you, our attendees, to consider presenting on one of your projects, leading a facilitated topic discussion. Maybe it's a discussion. I think the last one we had was about like lifelike actuators, and then lead a discussion about interesting videos. So, and then, of course, if you're watching this later on YouTube, same thing. Can everybody still see my screen just fine? Just making sure. It's a thumbs up or a yes.
Yep.
Okay, cool, thanks. The little, thank you. The little border around it went away. This is just some topics if we don't have anything to talk about, or just open topic discussions at ideas if you want to talk about them. I think they just normally sit here. Interesting robotic sensor technologies. How, well, you can read them. You know how to read, hopefully. This is our presentation plan. We have, of course, have the presenters for the rest of the year figured out. We have Matthew today with haptic and augmented reality systems. The barn, which is a Bainbridge Island. Oh, it says right there, Island Artisan Resource Network. It's kind of like a microspace, but it's not. They have some sort of presentation, I think, about the barn, if I'm not mistaken. Our very own Greg is going to have a discussion about behavior trees implemented in Gidget. And then Bob Higgins is going to do a presentation about processing computer vision data. And then, I'm not going to go with that. It's like Dr. Maddie Bar. Yeah, I'm sorry, I don't know. SLU student robotics project, so that's cool. But we have a lot of open projects for the beginning of next year. So please consider presenting on something. Maybe it's something you're building in your robot, or some other topic. And then, as always, after the meeting, there's a discussion if there's people around here to discuss still. If you want to discuss, that's fine, but I might make you the host of the meeting because once the host drops, it kicks everybody out. So the presentation coming up later today, or just in I don't know, 45 minutes or whatever it is. Matthew has discussion about haptic and augmented reality systems like we talked about. And he has a LinkedIn profile. Matthew, are you okay in the meeting if I share your LinkedIn profile, if I copy and paste that into the chat?
Yeah, no problem. Please.
Okay, thank you. I appreciate that. So looking forward to that. A quick review for the next month. Same Zoom meeting, same Zoom time. We always encourage you to check the SRS website for updates. That's seattlerobotics.org, I think it is. We should have looked that up. This is an ask from Steve. Help him find presenters. Send them to the email address. And again, always thanks for sharing in chat. We're always looking for people to drop stuff in chat if you got like something to add, something new coming up, even if it's not, even if it's adjacent, you know, if it's EV cars or whatever. Feel free to drop interesting items into the chat for others. Oh my gosh, we're already here. Okay, so here we are. We have around the web, if you will. If you have something interesting to share, please unmute now and share it. We'll wrap up around 10:55. James is going first. I saw your hand raised, and then as you see here, we'll get 10 minutes from 10:55 to 11. So, James, what's going on? Turn it
I
over to
just
you.
actually have a question. We're interested in adding some raw support for robot, and I'm curious. It looks like there's two different ways of doing that. One way is to provide source code for a driver that you then compile into your ROS control system on a PC, and then it would send out robot native commands. You would talk to the driver, via ROS, and then it would translate and send out robot commands, get back statuses, and translate those back into ROS. So it would be source code that you would add to your thing. The other way of doing it is to put like a ROS messaging layer on the robot, where it would then subscribe and publish topics and do like the translation into the robot control system on the robot. And I'm just curious if anybody has an opinion about which one of those is better. Maybe you can cast a vote in the chat or something like that. And that's all I had. Thanks.
Motion detected. Absolutely. Let's see if anybody has something to chat here. Yeah, I only have experience with ROS 1, though I'm starting to work on ROS 2. So it is a commitment, of course, because it really, if you've already got a communication layer in your robot system, it totally affects how your different portions of your robot communicate.
There's a lot of people still using ROS1, by the way. So just based on our survey, it's like adoption of ROS2 has not been anything like 100%.
Yeah, I mean, to be frank about it, I tried ROS 2 right away when it came out because I was getting into ROS 1. And ROS 1 was fine other than, well, ROS 1 had its own problems, but the its strength was it did easily through ROS serial talk to micros, and with that you could talk to sensors easily, like the lower end, the lower burden sensors, the time of flight sensors or whatever you were using. And you could do all the post or pre-processing in the microcontrollers, but once when it first came out, there was no solution, especially for like the low end microcontrollers, to communicate into ROS2, and they since have kind of got that fixed. I mean, you need a microcontroller that's got a little beef to it to communicate now ROS2, but it dissuaded me from continuing on, so I continued with ROS1 just because I could use the Arduinos or whatever, pick microcontrollers. But thankfully, they've since fixed that, I think, or at least somebody built something for it. I don't remember the name of the project. I should remember it, but I don't. Anybody else have something they want to share, or I'm gonna unleash some YouTube videos on you?
I'll share something.
Awesome. Thanks, Layton.
It was great joining for my first session last month. And I got to know Bernardo a little bit, who the fellow that presented last month on ROS2. And that was my first exposure to any ROS stuff. And I've kind of been going through getting started this week and got, Ubuntu fired up on a separate partition on a machine, and I've been playing around with ROS2 just a little bit. But the thing I was kind of interested in just letting you guys know about is I'm in a Discord with a bunch of robotics folks, in another area, and we discovered this NASA Summer Sprint Challenge, and it's essentially NASA has forked ROS2 into their own repo, and they've got a new repo called Space ROS, which is essentially obviously like specialized version for space applications. And right now, in their Gazebo simulator, they've got the Canadarm, like the ISS robotic arm, and they've got, I think, Curiosity rover in there. And essentially, I mean, that repo is brand new. There's maybe 380 commits in it right now. Like they're still doing bootstrapping tasks. And so this is sort of a call to the community to help improve Space ROS in general and their sim capabilities. So we spun up a team with, I think there's 7 of us in there, and we're working to try to we just decided last night on what our project is. What we're going to try to add in some sim capabilities around Starfinder, where you could basically, navigate on the moon, like you can get your position localization on the moon based off of field of view of a particular camera up against the stars. So just kind of an interesting, fun project that we're gonna attempt. I don't know how far we're gonna get with it, but we've got until September, I think 11th is the submission date. So that's the thing that we're excited to work on. And then the other thing I heard about from Bernardo was that SRS is doing a competition around maybe building a robot, I think. So I was interested in learning more about that. So I'd love to hear more about that if we're going to jump on that topic at all today. So.
Yeah, I mean, I don't know of any that specifically have us. I could have missed something, have us doing a competition around actually building a robot, but there are the 3 core SRS build challenges, I guess, if you will. And the idea between the SRS build challenges is that you're building a simple robot. Well, with build challenge 1, you're building a robot that can perform like some of the most basic of wayfinding missions. And the idea is like from build challenges 1, 2, and maybe 3, you could say you build up enough skill set just trying to build those robots to be able to participate in like the PopCan challenge or the Outdoor Robo Magellan, which are kind of each in their wayfinding competitions themselves. One's an indoor one, one's an outdoor challenge. And those, you know, well, the PopCan challenge usually runs like 3 times a year, 2 or 3 times a year for competition. One's up north, one's down south. Sometimes we do one kind of in between. It depends. But last year we did one in conjunction with like the war robot guys, you know, the guys that do the BattleBot stuff. And then Robo Magellan is once a year, and it's actually hosted by the SRS. The SRS hosts one of the PopCan challenges. But the build challenges are really, I mean, I really like them. We tried to start something up north with the Snohomish County Robotics group, where we were trying to help people start building their own robots. It didn't really catch on though. I think there's just not enough critical mass to get people. It's always like one, maybe two people trying to take the journey. And then everybody always seems to start out with like one thing that they're really good in, like they're really good in software, they're really good in mechanical engineering or whatever it is, and then they have to learn the other bits of it, which is the fun part about it. I mean, that's why I like robotics. I felt like I was very sufficient in electronics, but didn't have any CAD skills, and since I've bolstered those and other things, I also was a very low level assembly programmer, and that doesn't do so hot in robotics. So I forced myself to learn C finally. But the build challenge is like build challenges one. It's a very simple robot. It just has to go and perform a 15-foot square turn. You know, it turns 4 times on the corners, and the robot that lands where it began wins, whichever one lands the closest. So if you know, I don't remember how far off I was this last competition, but it was, I don't know, like 3.5 inches or something, which is pretty far away over 15 feet. So if you can pull off less than 3.5 inches, you would have won. And then my other ones were not as close. I think you get 3 runs at it, if memory serves. But the idea is like, you know, you could take a $20 robot off of Amazon and put some electronics on it. And you know, if you're using IMUs or if you're put a coders on it or whatever you're doing, you could build a robot that could win that competition. And you have a lot of foundational knowledge at that point. You've got a robot that can start spinning motors. Maybe it's looking at coders, maybe it's navigating against an IMU or whatever you used. And from there, you know, you can start building other ones. The next one is build challenges 2, which is out and back. I want to say it's like the rules say 300 feet. I don't think we do 300 feet at the field, because I think we only have like 150 feet or something like that. So we truncate it to 150 foot. I could be off on that one. I just don't remember as last year. But the idea is, you know, it's outdoor. Same thing. You're driving out over a rough area, over grass and, you know, holes in the grass and all that stuff bouncing around. You got to drive out there to that whatever mark it is, a couple hundred feet, and then back. Same thing. The robot that makes it closest back to its return point wins. And I learned the hard way last year that it sounds easier than it is, but my robot was bobbing me out on grass, and it stalled in the grass because the grass was, you know, it's summer. Well, it's late summer, but the grass is, you know, it's not like driving around on carpet. So my robot was not big enough to perform. John Jennings' robot did a great job, but he had like some weird compass error where he would return back and it would come off. It'd come back at like, I don't know what it was. It was like between 7 and 10 degrees off. And so it came back, and it came back the right distance, but it was way off in its from its starting point to its return point where it should have returned to. So kind of interesting competitions. And then they start adding in like it has to go around obstacles, right? Again, all things that are additive. So it is nice when you're building a robot to have those additive things. And all the competitions are built with some point-based mechanism, so you don't have to complete the entire thing to get points. And even the best of robots have mechanical failures day of. They get robotic cold feet and they have failures, and that allows somebody maybe new who has a robot that doesn't do as much but can do some of it to win. And really the competition's just a motivator to make you not delay so much about building your robot. So
Yeah, that's actually why I wanted to join SRS, because I was like, I'm the kind of person that needs other people to drive my like discipline to going after something. But if I have a team to work with or people that are doing a thing that I want to contribute to, then I'm way more likely to to jump in and do something. So,
Yeah.
is there info on the SRS site about those things? I actually can't find it in
Yeah,
there.
go to robothon.org.
Oh, okay.
I'll put that in the chat here.
Yeah, it's actually along the top bar of the.
Oh,
of
is
the
it? Okay. Yeah,
website.
robothon.org.
So,
So
okay.
yeah, that's
I'll check that out.
yeah, please do.
Awesome.
And then I recommend just diving in and signing up, and then you're kind of forced to bring something. I've signed up plenty of robots that did not go on the first day because whatever, a battery failure, a driver died, whatever stuff happens. But it's still
Yeah,
fun to come and show up and have fun. But
awesome.
performance anxiety, that is exactly right, James. I have a lot of robots with performance anxiety.
Well, thanks for the overview of that. That was very awesome.
Absolutely. Yeah, for sure. Thanks for the question. What about who else? Anybody have something to share? Anything you're working on? Anything you recently read or?
Yeah, this is Dick.
Hey, Dick.
Last month I showed something I was working on. I could give a little update on that.
Would love to see it. Yes, sir.
All right. I was having trouble with Zoom today. I start up the app typically, and I do it early because it always disappears. I presume it's doing an auto update. Then I come back and start it again, and then it's good to go. Well, so I went through that today, but when I tried to start it up, Windows couldn't find the app, the exe file. So now I am logged in through the web version of Zoom, and it kind of complicates things.
Yeah.
So, and for some reason, I'm not able to start video, so you won't be able to see me. But hopefully I can share my screen, which I will try to do now.
Please do. I'll stop my share just in case it conflicts.
Okay. Let's see. I guess that's the one I want.
It worked.
Okay. So I'm going to switch to a different tab here. So do you see that?
Yes, sir.
That's my 3Pi robot from Pololu. It's got an ESP8266 piggybacked on the robot. And these wires here there's one ground and the other's for transmit receive for serial communication between the ESP and the robot. And that seems to be working, but I need to review the software on both ends because I haven't looked at it for a long time. I just got the wiring for this fixed up. The interesting thing about this ESP thing, it's the software that's in it is something that I got. I downloaded a collection of applications and I tried one out. It had most of the features in it. So basically that's what I'm using now with some modifications that I put in for communicating with the robot. The interesting thing about this Wi-Fi is it can act as a Wi-Fi access point so that you can connect to it if you happen to know what the IP address is. Well, first you have to know the name of the access point. So you can connect to it with a cell phone or whatever. But the other side of it, it also acts as a station, and it connects to the Wi-Fi access point on my local network here. And that's what's set up now. So in the picture, you see there's a red light in there. I'm going to move that over a little bit. There's a button here. If I push that, it changes to green. Then it goes back to red when I push the button again. That's just kind of a test feature I built into the programming that I added. Now we'll look at a different picture. Now this is a web page that's served up by the EAP. So I added some stuff to it for testing. I've got a lot more I need to do to make, what's going on here. My screen just went blank.
Yeah.
No, it seems like it looks like it came back. So do you see that web page now?
Yep.
Okay. So the toggle button here, well, let me first say that the web page is being served up by the ESP Wi-Fi thing. And of course, I'm looking at this web page through my local network, which the Wi-Fi thing is connected to. So that's how I'm getting this web page. Now the toggle button the purpose of that is to toggle that light we looked at before on the other picture, the other tab on the web browser. So the toggle button, the purpose of that is to change that light. So when it says state on, that means it's getting a message back saying that it's in green now. Toggle it again, it's getting a message back saying that it's red. Now I'll go back to the camera so you can actually see the light. And I kind of have to, since I can't put both of these these tabs on the same vision, so I'll toggle this and go back here. Now you see it's green. Go back here, toggle. Go back here, it's red again. So that's kind of interesting. And if I were to connect to this with my cell phone, I could also toggle that light. We get the same web page. So the programming in there doesn't track, or it doesn't yet track where it's getting its input from. So that's kind of where that stands. Looking at here, let's see if I can select all. The Wi-Fi thing there is, I got some programming in it that response to commands. You see there's an up, kind of an up arrow and then an S. The command is S, just to sign on. And that'll tell me the version of the software that's in the Wi-Fi. The up arrow is to tell it to deal with that command locally. Without the up arrow, it would send it to the robot. And it's got its own command set, which I haven't been able to get to come back yet. So I've got to figure out that problem. Anyway, I'll send this command. So this is kind of what I call the Wi-Fi. And the last time I worked on it was in February. The other thing you can do with this, question mark, send, and it sends back a menu of the commands you can type in, or commands you can send. So it's mostly test stuff I got in there. There's nothing in the commands there to actually tell the robot to do anything. So, but it can be used as just a let's see. I'm gonna try doing this. Well, first, does any of that make sense?
Yeah. So are you're still, I think you'd mentioned you're still working on getting the command to pass through down to the 3Pi.
Right.
And
And
I'm kind of curious, if you don't mind, and particularly for the people that weren't here last month, is this just completely exploratory, or do you have like a goal for the robot, like its function?
yeah, I'd like to, I'd like to, put it in one of the contests, maybe just the one that does, runs around the square box. But right now, basically what I've got programmed in the 3Pi is things that will interpret commands and cause the robot to do things. I won't be able to demonstrate that now. That'll have to come later. But it's possible to type stuff in here and have it go to the robot, presumably. I just have to figure out why that's not working. So I'm gonna clear this again here. Let's see. Control A. Delete. Now I'm just going to take this out just so it's not confusing anything. Now what I will do is have to use a flashlight here. So the reset button in the Pi is way down on the bottom. But I guess I didn't get it. There. So that's a 3Pi sending over this serial to the Wi-Fi thing. And so that's its sign on, but it didn't do the whole thing. It's got some stuff cut off. So I have to figure out what's going on there. The programming in the Wi-Fi has got some data routing, and some of those commands in there and control the routing. So it might be something wrong there, because I did have a similar problem before. But anyway, so you can see the 3Pi at least sent out a sign-on message after reset, and the Wi-Fi caught it. So that's about all I can show now. But it's been kind of a challenge working on this thing.
Aren't they all?
I ran into an interesting problem is with the serial connection. If the two pieces are connected together, the Wi-Fi and the robot, through the serial lines, the Wi-Fi tends to get hung up and doesn't do anything. I think it's because, so that's if I switch it on and the robot is switched off, the transmit from the robot will be a low because its power is off. And the Wi-Fi, apparently the serial processing of the received can't handle that, and it just hangs. So I have a solution to that. In fact, I did the wiring of it. It's using well, it's kind of a bus driver with enables. So it's an IC that's it's got 4 bus drivers in it, and I'm only using 2 for the transmit and receive, connecting the 2 devices together. But it using the enables, when the enable is, or when the setting for the enable is disables the output, it's like the output of the bus driver is floating. It has no effect on anything it's connected to. So I'm using some trickery in there to try to manage this signal level, because the idle state of a serial connection is high voltage. And if there's a low there, that means it goes low only when it's transmitting data. So high is the default situation, and the low is what makes things happen. Anyway,
Funny, Dick, that you're working on a problem and having troubles with communications to microcontrollers. I mean, it's not funny that you're having to deal with it, but it's funny that's what really prompted some of ROS 1 being developed, communication between different systems and building like a common communications platform. I mean, a big part of having systems communicate with each other is the fact that every single time somebody has to build a robot, they have to build this whole, figure out the communication system, what is the protocol, then what are all the commands that are going to be shared, and agree upon some sort of common protocol.
right.
And that's why I think a lot of people did go to ROS 1. As a matter of fact, I always saw ROS 1 originally as like this big overarching, and it has like all the SIM and control modules and everything for demonstration, but really its function is communications. And I had the same exact experiences that you did. I was building my very first PopBot, and I actually ended up, because I was so frustrated, I went away from serial and I went to I2C master and slave, although maybe they've changed the name. I've seen a lot of places appropriately change their naming. Are you done with your share? I can take back over.
Yeah, I'm done.
Okay. I've seen a lot of places go to manager subordinate for naming, which is more appropriate these days. Go back here. But yeah, I went to that like I squared C protocol because I was having the same problems you were, and then you get problems like you know, if you're on different power buses, you're sharing the same ground. Can you share the same ground? That sort of thing. So that's
Right.
yeah.
Yeah, I prefer serial because it's, you know, it's asynchronous
Yes.
and it's very simple. But there's just this one issue that has to be dealt with. Because I want to be able to run both of these, the Pi by itself or the ESP, and I don't want to have to be plugging wires in every time I want to connect the two. If I could automate that, the fix for the connection problem, that's what I was after.
Yeah.
And I'm just at the point where I need to test that to see if it's going to work.
James has got his hand up if you don't mind. What's up, James?
Okay.
Thanks. Who was it that was using CAN bus? I'm kind of interested in that because I believe it handles high noise environments better.
It
I've seen
does.
some issues
Yeah.
on I2C with that. I think was it Greg who was using that, or was it somebody else? And whoever
Both
it
of us
was,
do. Yeah, Greg and I use CAN bus.
can you
for the
do a
same reason.
presentation, or did you do a presentation on how to set up CAN bus and how to get going with it? Like, especially in like the small microcontroller slash Arduino slash Nano sort of space.
Yeah, I've done one before. It was a little bit more off the cuff, but I'll talk to Greg and see which one of us wants to do it. We'll do that. That's a good idea. Absolutely.
Yeah, well, not we. I personally have done some experimentation with I2C and found that although it's really good and you can get it going really fast,
Yeah.
when you get it going really fast, the crosstalk is horrific. And
Yeah.
there was a lot of problems with just like clock signals introducing data signals and things like that.
Yeah, I mean, it was a protocol that was meant to sit on a circuit board, but now we're stringing
Right.
it a meter of wire modules, right?
Yeah, you're running it.
This is Dick. The problem with I2C is it's not hot pluggable. It's one thing I like about serial. One of the things I like about serial is you can hot plug serial links.
Yeah. Yeah, well, and I mean, CAN is hot pluggable, if you will. You can just plug into it, and the nice things about CAN bus is, well, it's not really it's not like there's a subscriber. You do usually set up your transceiver to filter out for the messages that you care about. So a lot of it's, you know, publish and not necessarily subscribe, but filter and ingest. So but yeah, we can definitely have a conversation about that. And you can plug in and out of the network. I don't know like that they would do that in cars unless there was like some sort of like auxiliary module you plug into, but it's extremely robust and it like you can run that all over. It's very noise tolerant. You can have addressing. And then, you know, there is a built-in, if you if you use it, you can set priorities, which is kind of nice for communication, which is really important when you're dealing with robots that work around other humans or work around humans, period. But not trying to dissuade you, Dick. I spent years and years of playing with serial. I absolutely love serial. It's a blast. It's easy to troubleshoot because you can plug in even an oscilloscope if you had to and look at like what's going on. You can grab like a RS-232 USB converter and like look at the data right off, looking at an application like real term so that you can just kind of like see what your communication is. Where once you start using CAN, then you need like a separate CAN bus interpreter, and then you need something that sits there and looks at it. And you basically like it's cheaper just to build your own CAN bus monitoring system, which both Greg and I have had to do, just because you're like, did it get the message? Did it send it? Or what message did it send? What kind of data did it include with the message? And then, again, it's like a protocol that, is variable length, and it's extremely flexible. And there are some kind of like there are some like protocols that are built on CAN bus that are meant for robotics, but mostly industrial robotics. So I think in both of our cases, we went our own ways, um, deciding what the communications look like.
Yeah, that's on a CAN bus, but that's as far as I went with it. But I have used I2C, with good results. But there can be an issue of if you lose a connection, the whole system has to reset, and the I2C communications has to be reestablished.
Yeah.
So that's kind of a big pain. If you've got things that are just interconnected and there's no plugging and unplugging, it's not a problem. But
Yeah, absolutely. You have to look for those errors or missing sensors and then restart the communication with the sensor if something happens. That happens every once in a while. My 8th generation Popbot has like a big RS, I think it's like a DB25 connector that connects the top side to the bottom side. And I2C does go through it. And I have to, particularly on the time of flight sensor that sits low, I have to look for a disconnection. And if I see one, if I see an error or if I try to like request some information, I get there. Actually, I have to sit there and trap and restart the communications on it just because maybe it was a bad connection or something like that. But to your point, and then to James's point, I mean, it is extremely sensitive to noise, particularly if you're running it fast. Like I went away from it on my original like Popbot 2 and 3 because I made my PIC microcontrollers. They were I2C slaves, and they were basically stepper motor drivers. They did all the control for my stepper motors, so I could send it like go this speed, and it would handle all the acceleration and everything on the PIC. But I was running the wires only like I don't know, like 18 inches or something like that from the Arduino or whatever I was using for the master. I don't remember, but it was going by stepper drivers, and there's stepper drivers are incredibly noisy electrically, and so I would catch errors or missing packets, so I'd have to like sit there and send them often so that they'd get through. Hello, never, I think. Any other last thoughts or questions before we go on a 10-minute break here before our presentation? And by all means, you can continue to talk. I think we will call it a 10-minute break right now. I'm going to go grab something to drink real quick. We'll start with Matthew, who's on at, I don't know, sometime 11:04, 11:05, whenever Matthew's ready. That's correct. They do start at 10. All right, so take a break. And I'll be back at 10:05 or 11:05 or so.
Do you mind if I put my slide on here while we're waiting?
Yes, I'm going to drop my chair. There.
Yeah, so one of the things I like about using Serial is that my Lab Nation Smart Scope has a decoder for it. Also has a decoder for I squared C and SPI. Um, so like I can hook up to it and just like immediately see what it is that's going on. At the same time, I can see like if there's crosstalk or if there's noise or whatever, I can see both the signal and I can see the decoding of that signal. So I understand like why it got decoded incorrectly. Unfortunately, they don't appear to have CAN bus decoder. They do have a system for adding decoders, but it uses uh, oh good grief, .cs is can't think of the name of the language right now. C sharp. So it uses C sharp, which I do not grok. That sucks. Is CAN bus a 3-wire protocol or a 2-wire protocol?
It's 2-wire, high-low. There's no ground that goes along with it. So it's different.
So it's a data and a clock type of a thing.
No, it's more like Manchester biphase-ish, if you will.
Oh, so it's two. Is it two single direction buses?
It's 2 wires. It's bidirectional. There's no ground. I think I mean, electrically, I don't know, but my presumption is it just uses the difference of voltage between the high and the low wire, the high and the low wire.
Okay, so it's a 1-wire bus. They have a 1-wire decoder, but it's the Dallas Maxim 1-wire.
Yeah, 1 wire. Yeah, and I wouldn't even call it 1 wire because 1 wire is not ground. The idea isn't that it's signal.
It's a differential.
It's a differential. Like RS-45. Well, it is very similar to RS-45, but
So it's basically I mean, it's a serial protocol with a bunch of like extra data on top of it.
Yeah.
So you could probably use just if you get the differential signal out, you'd have to have some kind of a little front end for doing that. And then you could use the UART decoder and look at the data, but it wouldn't then decode the protocol that's built on top of that.
Yeah, and I just came back and I think you were mentioning you have a logic analyzer.
It's a smart scope
Cool.
by Lab Nation.
Okay.
So it's a combination of a scope and a logic analyzer. It's a kind of it's a lousy scope and a lousy logic analyzer, but the combination of the two is really, really nice because you can see the analog signal and see the decoding of that signal right on top of each other. And so you can go, oh, it missed something in decoding right here, but look, that's because there was a big spike introduced from the clock line into the data line, and that's why it got that wrong, right? This is where my problem is coming. That has saved me. I can't tell you how many times. So
Yeah, I have I don't know how you pronounce it. Salier or something like that. Logic analyzer. I just dropped a link in the chat.
yeah,
A little on the expensive side, but I got them when they were cheaper. I don't know why they got so expensive, but they did. And it's nice because it's a good logic analyzer, terrible scope. It just does like 0 to, I don't remember what the max safe signal is, like 5 or 7 or something like that. But it is nice because it also has the protocol analyzers in it. And it says it does CAN, but I have never gotten into work with CAN bus. I wanted it to. But yeah, like you said, I squared C is great. The serial is absolutely fantastic. It does an auto bot detection, which is does a really good job of it on serial, which is nice because and I'm sure with the work that you've done, you've probably set up fuses inside of microcontrollers to set like the speed of the micro. And I tell you what, when you're working in assembly, the number one thing I'd mess up every single time it seemed like was getting the oscillator right, and then like all the baud rate, all the registers set to get it to the right bundle.
yeah.
The baud rate's like 7412 or something weird because you set up the device wrong and everything.
Yeah. Yeah, I've yeah, I have too many stories to tell about that.
Yeah, I feel the pain in in your response, and I know what you mean. Like you're like,
Yeah.
what in the world is going on here? So sometimes I would set it up specifically just to like spurt out the hello world, so I could
So you
get
could see
out.
what's going on.
Yeah, I'm like,
Yeah.
oh, I'm like double the speed. Okay, I got it. I know what's going on now. That's what
I
my
always send out AT,
oh
capital A, capital T, because
yeah
that gives you all the information you need
yeah
for anybody who's old enough to remember the old modems. There was a
yeah
reason why they used AT commands. It's because
yeah
it's a two different bit patterns, on off and then off on the other one, back and forth, and you can get
yeah.
the baud rate from it really
Yeah.
clearly.
That's
You can
clever.
see
I
where
never
it
considered that. Yeah.
yeah, you can see where it transitions from the A to the T, and so you know right where the character starts and the character stops, and you can see the pattern just going on and off and on and off and on and off on each one of them. So it's a pretty unique identifier. And then if you just like count the bits per second, do a little math, you got the baud rate, and then you can auto baud rate detect. But I mean, in my case, I would just look at it and go, that should have taken this many or microseconds, and it took this many microseconds. So
Yeah.
I know I'm on.
Yeah.
And keep dorking with it until it's right.
Yeah, absolutely. And I wish I had a logic analyzer that had well, I wish I had a scope that had a better logic analyzer. I even have a decent scope, but like I have a 2000 series Tektronix and it has a logic analyzer. It's an MSO, but and I guess
Yeah,
I would
I really recommend this Lab Nation.
yeah
If you get a chance, it's like
yeah I
200
will pick.
change. And
Mhm.
you know what I like about it the
You have a
best, to
link
be
by
honest with
chance?
you? Huh?
Do you mind dropping a link? So
Yeah, sure. What I like about it the best is actually the user interface,
mhm.
because it has this really cool, like first off, it'll work on an Android device, it'll work on an iOS device, it'll work on a PC, uh, any operating system. It's very complete support, and it has a touchscreen interface where, like, normally with a regular oscilloscope, you're like sitting there spending all your time figuring out which knob to diddle in order to change whatever parameter it is that you want to change. And like, I used to have this Tektronix oscilloscope, and you like had to keep pushing these buttons to go through these menus to get the knob to then do the thing that you wanted to do. I'd spend so much time just trying to, and so with this Lab Nation thing, I can just like put my fingers on the screen and spread, and it zooms in, changes the time base. And I can like scroll left and scroll right with one finger. I can move up and down. I can easily set uh, the, all of that kind of. I just love it.
We're chewing
Finish
into
this comment
Matthew's
really quick.
time, so I'm
There's
gonna
the
let
Lab Nation.
Matthew have it, but I'll look for that link and yeah, absolutely.
Yeah, I posted it just now. I was
Okay.
just finishing up a comment to Nabber about trying to do a cardboard combat league. For whatever reason, I just like could not get any interest in that whatsoever.
The LinkedIn link going out right now, and we'll send it over to you, Matthew. Thank you.
Hi. Yeah. Well, thanks for the opportunity to talk here. So when I was invited to give my presentation here, I was actually a postdoctoral researcher working in the Query Simpson Institute for Bioelectronics with Professor John Rogers. As of 2 weeks ago, I'm an assistant professor at Georgia Tech, and so I'm still getting moved in here. I'm basically surrounded by a bunch of moving boxes, and I'll tell you about my research, which is about neural mechatronics and extended reality for patient care. I have time here for questions, and so if you want to interrupt me, if you want to wait till the end, however you guys usually do it, please feel free. And so I'll talk a little bit about the work I've done starting from my doctoral research, which I did at MIT with Professor Jung-Yoon Han. And then, like I said, I worked with Professor John Rogers as a postdoctoral researcher, and a lot of the work I'll talk about is going to be the work I did in his lab. So I'll start here if this will work. I'll start here with the motivation for my research, which is neurological disorders. So these disorders present an immense societal burden, and current interventional methods don't address a lot of the problems we're currently facing. This has only become more and more consequential as the population has been aging. And so this video I'm going to play here is showing a patient that I saw recently. And actually, it's telling me I can't play videos. Let me just try 5 seconds to enable it. If that doesn't work, we'll just move on. So I guess I can play it like this. So this is a patient that I saw recently as part of the clinical trials that I'm leading to help people that have conditions like stroke and spinal cord injury. This patient had a stroke. And because of that, he has a number of motor and sensory symptoms, which makes it very hard for him to walk around in his daily life. And so I'm developing a system that's designed to help people that have these type of motor and sensory symptoms. So this table on the right is showing 5 of the most common neurological disorders currently affecting people in the United States. So stroke, spinal cord injury, tension type headaches, epilepsy, multiple sclerosis. I've had the opportunity to contribute to solutions for most of these conditions, and I'll talk to you a little bit about that today. So, sorry, just trying to get it to move.
PowerPoint.
Yeah, I'm sorry.
Oh, it's okay. I've been there, I've done that for sure.
Well, we'll restart it. It should just take a second.
Okay, PowerPoint's a new program. They're working on the stability still.
Yeah, yeah, right. Exactly. So, let's see. And basically, you know, what I'm trying to put together here are these neural interfaces. So neural interfaces have been developed for both the peripheral and the central nervous system, despite the fact that there's a lot of really promising applications in the peripheral nervous system. A lot of the focus so far has been on the brain and the central nervous system. And so my research is focusing especially on peripheral neuromodulation technologies. So I'll start by overviewing some of those kind of present and emerging methods. Electrical stimulation is by far the most mature. This is used, for example, in Neuralinks technology. And unfortunately, we have these trade-offs in terms of the selectivity and invasiveness of those approaches. Generally, we want a very selective interface. We want to have something that has a lot of resolution, which can help us, amongst other things, avoid adverse effects. But we have, when we, you know, as you can see, as we have a more selective interface, we're compromising the invasiveness. It's less stable, it's less safe. And generally, the goal of my research is to develop solutions that are non-invasive or minimally invasive, but are highly selective. And so this slide on the left is showing some of the other current methods which kind of are emerging, including magnetic field-based modulation, ultrasound, infrared. And these are offering are non-invasive solutions which are offering some degree of selectivity. And so again, the goal of my research isn't focusing on those in particular, but with a similar goal, developing non-invasive and selective interfaces. So this is what I'm going to talk about. So first, what I did in my doctoral research was these iontronic peripheral nerve interfaces. This is going to be a little bit biology centric, and so it might be a little bit off the expertise of some of the people here, but I'll talk about how this kind of plugs into the rest of the talk, which might be a little bit more relevant to what everyone's working on, which are these multimodal haptic interfaces, which are essentially a way of interfacing with the peripheral nervous system non-invasively. This is what the work I did in my postdoctoral research. And as I'll talk about, I would describe this as a robotic system in the sense that we have actuators, we have sensors, we have a control system. And the goal here is a little bit different, but a lot of these techniques might be relevant and interesting to some of the stuff people are working on. And then finally, I'll talk about this kind of last area of research, which is ongoing, and it's basically applying those haptic devices to these clinical trials, which is designed to help people that have these conditions like stroke and spinal cord injury. And so, again, I'll start here with the work I did in my doctorate. This is these iontronic peripheral nerve interfaces. So, the most common way of treating diseases in humans by far is taking pills. But with systemic administration of a pharmaceutical agent, it's really hard to control exactly where and when that agent is having an effect on the human body. And so more recently, investigators have introduced these implanted drug delivery platforms, which can locally modulate the concentrations of different chemicals. And so one of those platforms is shown on the left here. We have those three key elements. We have a pump, which is driving a therapeutic agent, some chemical, out of an internal reservoir, which is being gated by some type of valve. And what I'm showing here on this slide in particular is a technique called electrophoretic delivery. And in this case, we have a charged agent. We're driving it out of that reservoir using an electric current. The fundamental challenge of these implanted drug delivery platforms is that they rely on a finite stock of a therapeutic agent. And when that stock runs out, that device needs to be physically accessed so that it can be refilled or replaced. And so the approach that I helped pioneer in my doctoral research was ion concentration polarization with ion selective membranes, which essentially offers a way of remotely refilling the internal reservoir. And this is the subject of these 6 papers. And I'll kind of go through what they talked about here. So the key element of this system is a material called an ion selective membrane. Essentially, this is a filter that we can make selective for specific ions like calcium, sodium, and potassium. Those ions are normally present in our physiological media, in our blood and our tissue. And basically, this filter can selectively pass through. This illustration is showing a membrane that's passing through calcium while blocking those other ions. And so when this is used as part of this drug delivery system, as shown in number 1 on the left, this operates very similar to that electrophoretic delivery, which I described on the previous slide. So we have a charged agent. We're driving it out of the internal reservoir using that electric current, and that's causing that agent present in the internal reservoir to be enriched locally in the volume around the device. But then with this membrane-based system, as shown in number 2, when we reverse the polarity of current, we can pull those ions back into the reservoir. And since it's being filtered by that ion selective membrane, we can selectively pull back that therapeutic agent. And so this is designed in particular to be compatible with ions that are present in normal physiological media. And so, like I mentioned, these ions like calcium, sodium, and potassium are present in our normal matrices, and they have their differences in concentration have a huge effect on biological and especially neurobiological tissue. And so we'll look at how exactly I use that here. So the starting point for this research was very fundamental investigations into the physics of these processes, which involve detailed numerical modeling. And what I really want to emphasize here on this slide is the parallels between the transport in the system and what happens in semiconductor devices. So in semiconductors, we have electrons and holes moving around inside of some solid state material. In this system, we have these ions like calcium, sodium, or magnesium that are moving around freely inside of an aqueous media. And so we have drift, we have diffusion, but instead of processes like recombination, we have these other features like partitioning and reaction. And so those constitutive equations give rise to the physics of this ion selective membrane transport system, which is shown schematically at the top of the slide. So basically we have an ion selective membrane, and then it's flanked on either side by 2 aqueous regions. One side might be the internal reservoir of the system. The other side might be the external tissue environment. Inside the membrane, I have a chemical called an ionophore, which is essentially binding with our targeted ion. And in this case, that's going to be calcium, binding it with a high affinity. And so basically making it the majority charge carrier inside the membrane. And so when we pass a current across that membrane, that current is going to be carried primarily by calcium. And that's ultimately what drives the enrichment on one side of the membrane and depletion on the other side. And so if anyone's interested in reading more about that, please see these publications I have here. And ultimately, this culminated in this PNAS article, which essentially is about applying that electrochemical system to an implanted peripheral nerve cuff electrode, which I tested in vivo in a rat sciatic nerve as a model for diseases. And so a cuff electrode, it's very simple. Basically, it's a tube that has a slit cut in it. It has these electrodes printed on the inside. And these are a relatively common tool in peripheral nerve interfaces as a way of stimulating those peripheral nerves. And so the goal here was to design a system that was capable of modulating the concentration of ions. In this case, it's calcium. And I'll talk on the next slide why calcium was chosen in particular. But the goal was to deplete calcium. And so I designed this cuff basically as a way of focusing the effects of calcium depletion within the confined volume of that tube. So that figure on the left, on the top, is showing a simulation showing how that calcium is depleted over the course of a few minutes. And so this was confirmed with direct electrochemical measurements. And ultimately, as you can see on the bottom left, this cuff is multimodal in the sense that it has one uncoated contact, which can deliver direct electrical stimulation. And then it has the green contact is showing the ion selective membrane coated contact, which can deliver that ion concentration polarization. And the idea here is that we can take advantage of the direct spatial selectivity of electrical stimulation combined with the functional selectivity of this ion concentration polarization. And so this is what that cuff electrode looked like. We have on the left a picture of that cuff electrode. It's kind of on the scale of a few millimeters, and that's going to be wrapped around a peripheral nerve. And on the right, you'll see what the cross-section of that cuff looks like. And during the operation, we're going to get depletion of calcium throughout that cross-section, which again is intended to have some functional effects on that nerve. So this is the experimental setup that I used for this study. So what you're looking at on the left is a rat. What you're looking at is basically the sciatic nerve of this rat exposed through the rear hind limb of the animal. And so you can see the sciatic nerve through that window there, and then you can see the cuff electrode, which with those wires poking out of it. And on the right, you'll see the schematic illustration of where that cuff electrode is located relative to some other important anatomical locations. So that cuff electrode is implanted just proximal, just before the nerve's distal trifurcation. And that trifurcation is where the nerve splits off into those three downstream branches. So your sciatic nerve basically starts kind of around your back, goes through your leg muscles, and then as it goes further towards your feet, it kind of branches off and gets kind of into these kind of tributaries, which are innervated other important muscles, other important sensors. And in particular, some of those muscles include the tibialis anterior, the gastrocnemius, which is our calf muscles, and the biceps femoris. Those are three muscles that we, both humans and rats, have. And as part of this experiment, basically I have these needles, these conducting needles inserted into each of those muscles. And so I'm performing what are called electromyographic recordings, measuring the electrical activity that's being generated naturally by those nerves. And I'm doing that simultaneously while delivering current and modulating concentration where that cuff electrode, you can see that being located. The reason calcium was chosen for this study is based on the biophysics of ion transport. Calcium depletion should lower the threshold of electrical stimulation. And so basically, sorry, let me just make sure I have this. Basically, what I want to study here is whether calcium depletion is going to lower the threshold of this nerve. And more importantly, what I wanted to study here was whether calcium would have a selective effect on different parts of that nerve. So on the right, you're looking at the cross-section of that nerve around where it's implanted, where the cuff electrode is implanted. And so you're looking at those three bundles, those three fascicles, which are essentially bundles of axons. All those axons are the basically unitary cells that are what are going to your different sensors, different muscles. And if you remember at the beginning, I kind of talked about one of the motivations of neural interfaces is we want a very selective interface. Generally, we have a relatively large neural interface, and we want to have some selective effect on some focal area of tissue. And so, for example, we might want to deliver electrical activity specifically to just one of those three fascicles. For example, if one was going to one muscle and that's what we wanted to trigger, then being able to selectively activate that is really valuable. And so what I wanted to study was whether this calcium depletion would selectively affect those different fascicles. And ultimately, that would allow us to basically increase the selectivity of this electrical stimulation. So this is what the results of one of those experiments would look like. So again, this was studied on rats in vivo, which means they're anesthetized, but they're alive. And what I'm measuring here in each of those three graphs. So first of all, each of those rows corresponds to the three muscles that I recorded from. So each of those muscles had needles inserted into them, and I'm measuring them simultaneously while delivering increasing pulses of current through the cuff electrode. And so on the x-axis, you're looking at the amplitude of current that I was delivering, and looking at on the y-axis how much EMG signal is being elicited for those increasing pulses of current. And what we see is this saturating sigmoidal function, which is characterized by this threshold. And what I'm looking at here is especially where that threshold is located and how it shifts to the left or to the right as a result of this calcium depletion. And so the red curve is showing the threshold measured before calcium depletion. The blue is showing the threshold measured after calcium depletion. And we see this shift in all those muscles. We see a shift in the threshold to the left after we perform that depletion. The green then is showing the threshold measured 5 minutes after turning that depletion off, and we start to see that threshold return back to normal. One of the most important things, again, that I'm looking at in this study is not just whether we can deliver that effect, but whether that effect is going to affect those three muscles differently. And so these are the combined results from all of the 8 rats that were studied here. Again, we have gastrocnemius, biceps femoris, tibialis anterior. The blue bars are showing the average relative change in threshold measured after calcium depletion compared to before calcium depletion. And confirming the initial hypothesis of this study, we see between a 30 and 60% reduction in that threshold. The green bar is showing the relative change measured 5 minutes after that. And again, that starts to return back to normal. And then those yellow and orange bars are the controls. And since we're not delivering any calcium depletion there, as we expect, we're not getting any change in the threshold. The most important thing I found in this study is that, as you can see, there is not a statistically significant difference between the gastrocnemius and the biceps femoris channels. But we do see a significant difference between those channels and the tibialis anterior. And to explain why that might be the case, I have the anatomy shown here. Gastrocnemius and the biceps femoris are both innervated by the tibial branch of the sciatic nerve. The tibialis anterior is innervated by the common peroneal branch. And so the results that I have here provide evidence that calcium depletion had a selectively larger effect on the tibial branch relative to the common peroneal branch. And the reason this is important is because functional selectivity has been shown to improve outcomes for clinical modalities like vagus nerve stimulation. And so someday this could be used to help people that have conditions like epilepsy. So that was the work that I did in my doctoral research. And one of the key observations that I had for my doctoral research was the importance of the peripheral nervous system and the untapped potential that exists in interfacing with the brain indirectly through the peripheral nervous system. And so the direction I took in my postdoctoral research, working with Professor John Rogers, was to develop somatosensory interfaces as a way of completely non-invasively but highly selectively interfacing with the peripheral nervous system. This is an area of research that my colleagues and I describe as epidermal virtual reality. The idea is that we want to reproduce a realistic and immersive sense of physical touch in a wearable device in an analogous way that a VR headset like Oculus is trying to reproduce this realistic and immersive sense of visual stimuli. Our skin is similar to our eyes in that our eyes contain multiple different receptors that are sensitive to different wavelengths of light. And that's our basis for color vision. Our skin also contains multiple different receptors. We have sensors that are sensitive to heating and cooling, for example. And then we have we have a range of different sensors that are sensitive to different types of mechanical stimuli. There's not just one mechanoreceptor that's sensitive to all types of physical touch or vibration. We'll have some types of cells that are sensitive to vibration, which is very important for perceiving textures, like if I'm moving a cloth around my skin. And then we have other cells, like Merkel cells, which are sensitive to low frequency pressures. And those are really important for detecting the shapes of objects and the directions of forces. And so the goal of my research was to develop a small scale mechanical structure which could selectively render sensations to those different afferent channels. And those types of engagement are shown on the right of the screen, having indentation, basically poking perpendicular to the skin surface, shear force, rotation applied parallel to the surface of the skin, and then vibrotactile, vibrating the skin surface. And so I was able to create a very small scale mechanical structure, very small transducer, very low energy, but can deliver a very large amount of force. And compared to current alternatives, the most important thing is that it's completely untethered. It's not wired to any external power supply. And so this is currently conditionally accepted in nature. And so eventually you'll be able to see this in press. But before I talk about how I kind of solve these problems, I'll talk about what those current alternatives look like. So the haptic device that most people are going to be familiar with are vibration actuators. And generally, vibration is the easiest and lowest energy way of delivering a perceivable sense of touch to a wearable device. And so you'll find these in your smartphones, Xbox controllers. But of course, as I talked about, we have more sensors than just those vibration sensors in our skin. We also have those that are sensitive to lower frequency pressures. And if we only have, vibration, basically, it's kind of like having grayscale vision. And so we also want to be able to deliver those lower frequency pressures. The problem is, the challenge here is that requires a lot more force. So you basically need to get a perceivable sense of touch for vibration. You only need to deflect the skin by tens of microns. But in order to actually feel, like if you're poking your skin and holding it there, in order to actually feel that, it needs to be indented on the order of about a millimeter. And that requires a lot more force, a lot more energy. And so the devices that are able to do that are generally very bulky and they're tethered. So one of a recent approach that's getting very popular is what's called hydraulically amplified electrostatic actuators. And basically they have some, very strong properties. It's not as strong, doesn't have as much extension as the actuator I'm going to talk about. But for the same size, it is a very high energy density. The main problem with this approach is that it requires huge voltages to get those changes. And so you need, those are, sorry. And so you need huge voltages to generate that, which are usually you need a benchtop power supply. Another popular approach are these pneumatic systems. So Meta's Reality Labs, for example, has a pneumatic glove. And generally, these are also tethered because they require some external compressed gas cylinder or some series of pumps. This particular image I have here is showing one where those pumps are built into that glove, but obviously that's very bulky. And so that's also going to limit some of the applications that we can use this type of technology for. We've seen some really promising results from these clinical applications of the device. And part of my ongoing research is to help people that have other types of sensory impairments, in particular, people that have conditions like stroke and spinal cord injury. And so this is part of a clinical trial that I'm currently leading to help people that have those conditions. And this is a video that I'll play, and this is a patient who we saw recently who has spinal cord injury. This patient is very similar to a lot of the patients that we've seen in this study. And by the way, this is done in collaboration with my clinical collaborators at the Shirley Ryan Ability Lab, Arun Jayaraman. And this patient is very similar to a lot of the patients we've seen in that she has a relatively good, she's at a very relatively late stage in her recovery. She has some motor control, but she has very little sensation below her waist. And, you don't really appreciate how important that sensation is for motor activity. And by the way, there's a huge variation, when you have an injury that affects your spinal cord. There is huge variations in how that's presented. Sometimes you have, more sensory abilities, but very little motor control, sometimes the opposite. This is designed in particular for people that, might have some motor control, but again, have some challenges with that because they're missing that sensory component. And there are similar symptoms that happen in conditions like stroke and diabetic neuropathy. But this particular patient and other patients as well, one of the ways that she compensates for her loss of balance is with her vision. She really relies on direct line of sight vision with her feet. And if she doesn't have that, she loses her balance pretty quickly. And so you're in that video, you watched her perform a task where I asked her to balance with her eyes closed. And as you saw, she could only do that for a few seconds before she needed to grab the railing. And so what she tells us is that when she's at home, she actually doesn't need any aids to walk around. But when she's out in public, she generally uses a wheelchair. And amongst the reasons for that is that she needs to use her eyes for other things. If you're crossing the street, it's definitely a hazard if you have to watch your feet while you're trying to cross the road and navigate traffic. And so the system that I'm designing is what's called a sensory substitution system. We have patients that are missing their ability to feel in their feet, and we're substituting it by delivering that sensation to a different part of their body. So I'll talk about what that system looks like on the next slide, but stroke patients are another important population that I'm looking at here. Stroke tends to be very unilateral, which means that the symptoms are primarily affecting one side of their body. And so one side they'll be able to operate very normally. The other side might have very minimal motor control or sensory ability. And so as part of this study, this is showing the distribution of pressure that one particular stroke patient was putting on their foot while we're performing this task where I'm asking them to, in this case, put pressure on their toes. They think they're putting pressure on their toe. We can see very clearly from these sensors that they're putting pressure on their heel. And so this system that I'm designing is designed to help with this type of symptom as well. And so these pressure distributions that you're looking at are being recorded from these sensors, which is the first half of that sensory substitution system. That's shown on the left of the screen. And so that's an array of pressure sensors, which is embedded in the patient's shoe. That's measuring the distribution of pressure that they're putting down in real time as they're walking, as they're balancing. That's connected by Bluetooth to this other device and is projecting that pressure distribution in real time onto that haptic device. And that haptic device is very much related to the device I talked about in the previous section. This is designed specifically for vibration. And basically, it'll deliver a pattern of vibration in the same pattern of pressure that the patient is putting on their shoe. And the idea here is that the patient would be able to intuitively perceive that pattern of vibration as that missing sensory information and use that to help them, substitute that sensory ability and use that to help them to address some of those sensory and motor symptoms. And one of the things that this study looked at in particular was how this might be used to help improve these patients' ability to balance. And so these are the results from one patient that I saw recently who was performing that task that you saw a video of in the previous slide, where I'm asking them to balance with their eyes closed. And we see this consistent improvement in this patient's ability to balance when they get this feedback. And so we've seen some very promising results from this study. And again, this is ongoing, and so please stay tuned. And so again, I started by talking about these iontronic peripheral nerve interfaces, and this basically electrochemical modality that offers a way of pulling different levers in the peripheral nervous system, or really in any neurological or biological tissue. And in particular, showing how this can be used to increase the selectivity of electrical stimulation to this particular peripheral nerve, as a model for other diseases like potentially epilepsy that could be used to help that condition someday. And then I talked about the work I did, especially in my postdoctoral research, which was these multimodal haptic interfaces, which again offer a way of completely non-invasively but highly selectively interface with certain parts of the nervous system. And then finally, this third area of research that I just talked about, which basically applies those haptic devices to these ongoing clinical trials, which I'm hoping is, currently is helping these people that have these conditions like stroke and spinal cord injury. And so I'll just talk a little bit about kind of some of the focuses and kind of challenges that I'm currently addressing in my independent research program, which I'll link to at the end of this slide, at the end of this presentation here. But kind of going back to the overall motivation here, our skin is, of course, our largest organ, and we have sensory receptors distributed throughout its entire surface. And so when we think about how we should be designing interfaces for our skin, we need to consider a few factors. It's very distributed, right? It's covering our entire skin, but it's also very sparse. We're not using all of that information all the time. For example, we're constantly in contact with our clothing, but we tend to ignore that information because it's not very useful for us. So in contrast, sensory modalities like our eyes have very focal concentrations of receptors, which are located in the back of our eyes. And so, we have this in our skin, we have this huge source of sensory information, which is really being underutilized in favor of other modalities like hearing and vision. And so we need to think about how these different modalities are actually, being recorded so that we can actually develop interfaces that can work properly. Because when we think about our vision, when we want to create an immersive, realistic sense of vision, what these VR headsets are doing are essentially just putting two displays right in front of our eyes. And that's very, very effective at be able to deliver that realistic visual stimuli. And what right now the frontier is figuring out how to expand this to other sensory modalities. And there's this huge opportunity for our skin because, especially for these sort of mobility and accessibility kind of applications, we don't want to encumber things like our eyes when we're, walking around and trying to, detect things that are in front of us. Our skin is an area where we might be able to apply more bandwidth as a way of substituting our kind of missing sensory information. So on the right, this is showing a commercial haptic device. This operates very similar to that headset in that it's very focal. This is a glove-based system. Most haptic devices, both commercially and research, are glove-based. And of course, our hands are a really important part of our somatosensory system, our ability to feel. But, with the same problem as those VR headset, being that we need our hands for other things. And so those, giant boxing gloves you see there aren't going to be very effective for realizing, a lot of these applications. And on top of that, it's tethered to that huge power supply. And then that itself has to be tethered to, a huge workstation computer. This is the current state of the art in VR haptic devices. And so the goal of my research is to develop systems that can address the sparse and distributed nature of our skin, as a way of solving these problems, something that's untethered so that we're not, limited by these different features. And so we haven't seen these haptic devices attract as much attention as VR devices have. And I think solving those problems is the key to attracting much broader interest and breakthrough, and attracting a lot more interest in these technologies. And so that's what I want to do with my research. And I would just want to finish by kind of talking about some of the challenges in this area of research as it relates to diversity, equity, and inclusion. So one of the huge major challenges right now in medical research is underrepresentation. Women, for example, are historically undersampled in medical research, and that has a huge effect on medical outcomes. And so when we think about this in the context of these haptic devices that I'm creating that use the skin as an integral mechanical element, if I wasn't sampling from both men and women, obviously this would have a much lower impact. That's really important. But I think we need to think about representation at all stages of the scientific process, not just kind of at the end as an afterthought. Even just conceptualization, thinking when we create these things, because it's very easy to create systems and devices that we think are going to work. Maybe I think somebody is going to work for this stroke patient, but you don't actually know what they need or what they want until you actually talk to them. And so a really important part of this process was integrating those patients very early in the design process, not just projecting what I think they want onto what we're trying here, but actually interviewing them and seeing what they want and what they need, because obviously those can be very different. And not only do I think this can be a great way of helping improve representation ultimately in the scientific process, but this definitely introduced ideas that weren't considered at the onset of this project. And so this was a really important part of this approach and should be considered broadly in how we do these things. So this is a project that I'm actually currently working on with my wife, who is a researcher in math education. So she helps teach students, for example, in this gentrifying neighborhood in Brockton, Massachusetts. And at the time, I was working on these augmented reality tools as part of these haptic systems that I'm working on. And we sort of collaborated to solve this problem where some of these kids are struggling to learn some concepts of math in kind of the middle school age and elementary age kids. And so I developed this smartphone app as a way of helping kids learn some concepts of area and volume. And so I'll play a screen recording from one of the students who's using this. And what you're looking at in the middle is the screen recording of the app as he's using it. He's going to tap on the screen to add these boxes, and he's doing that as a way of measuring the volume of that air conditioning. So I'll let him sort of talk.
Okay, Leslie here trying to find the volume.
Those boxes are, maned, tethered.
How's it doing that?
Are tethered to the real world, using that augmented reality system. And so we can tap to put those boxes.
I figured it out.
Then what's the volume of that?
And we found this was a really effective tool in helping students like this kind of engage with this a lot more. It's almost kind of like a video game, and so you know, it made him kind of the task more enjoyable to visualize those concepts. And so one of the things I want to emphasize here is, you know, this is another example where this is a relatively simple solution. It doesn't require, you know, any haptic devices or anything, but just by talking with the community that I'm developing this solution for, I can create this very effective approach. And so we should always kind of consider who we're designing these things for when we're putting them together. And so if anyone's interested in reading more about these projects, please see my peer-reviewed publications. They'll be on my lab website, which is listed at the bottom of the slide here, flavinlab.io. Please feel free to reach out to me at my email address. And just as some brief acknowledgements, I was funded in my grad program through a fellowship from Draper, in my postdoc through the NIH fellowship. I couldn't have done this without my clinical collaborators, especially at the Beth Israel Deaconess Medical College, at the Shirley Ryan Lab. And I did this with my mentors, Professors John Rogers, Jung Yoon Han, Sam Lin, Charlie Sandrello, and I definitely also couldn't have done this without my mentees, including Tara Saxena, who worked with me throughout my postdoctoral research. And so I would love to answer any more questions if anyone has some.
Thank you, Matthew. That was that was just incredibly amazing and very impressive. I have maybe a question that's silly and small, but in your actuators, I'm curious, you know, you show that you have some potential energy there. Is there any thought in the future, or maybe you did it and you just didn't include it because, you know, you only had an hour or whatever, to recover some of that stored energy from the skin being pressed in? I know some of that energy is well, I guess the equation was kind of balanced out. You didn't have to add any more current, as you had mentioned, but it looked like there was a little